Good day. Not too long ago I did a video on the complete iNav setup for Betaflight pilots. You can check it out through a link in this video's description below. Today I thought I'd take it to the next level in autonomous flight capabilities with ArduPilot, specifically Arducopter. That's right, we're going to put Arducopter firmware on an FPV drone and see what it can do. I'll show you some similarities between Betaflight and Arducopter, and we'll take a look at some ArduPilot hardware requirements for the Arducopter firmware on an FPV drone. We'll also download and install the ArduPilot Mission Planner, flash our ArduPilot flight controller with the ArduPilot firmware, and go through the complete Arducopter setup using the ArduPilot Mission Planner. We'll finish up with a test flight of our new Arducopter build to check out some of the ArduPilot autonomous flight capabilities. From firmware flash to flight, this is your complete ArduPilot setup for FPV drones. So first of all, what is ArduPilot? To some of us it may sound complicated, but that's only because we may be unfamiliar with it. So let me briefly explain. ArduPilot is an overarching or umbrella, open source, free suite of tools for autonomous navigation of different types of unmanned vehicles like airplanes, copters, rovers for both land and water, submersibles, and antenna trackers. This suite of tools consists of software, hardware, and firmware. For today's video, we'll be focusing on the copter subset of the suite of tools, and we'll be going over the software, hardware, and firmware for it. Earlier I mentioned there's some similarities between ArduPilot and Betaflight. Just as you have the Betaflight configurator, which is open source and free, to update your quadcopter's flight controller Betaflight firmware, we have ArduPilot's Mission Planner, which is used among other things to configure and update your quadcopter's flight controller Arducopter firmware once previously installed. If you haven't already noticed, this is a very similar process to updating your transmitter's OpenTX firmware with OpenTX Companion, or using the ExpressLRS configurator to update your ExpressLRS hardware. So once you get familiar with one of these processes, the others should come to you more easily. Now that we have a better understanding of what ArduPilot is, let's go to the ardupilot.org site, which I'll link to in this video's description below. The top of this page talks a little bit about the hardware, firmware, and software. The hardware consists of your flight controller and peripheral devices and sensors such as a GPS module, barometer, and compass. The firmware is the code running on our flight controller. In our case, it's going to be Arducopter for our FPV drone. This is just another firmware like Betaflight, EmuFlight, iNav, etc. to flash to your flight controller. The software is our interface to the flight controller. As mentioned previously, it's similar to the Betaflight configurator for Betaflight firmware. However, it's called Mission Planner for our Arducopter firmware. When we scroll down, we see this quick start section that outlines the basic process that we'll be demonstrating in this video. By the way, over here on the left is a donation button you can click on to help support further development of the ArduPilot project. So back to quick start, we see our first step is to select our vehicle type on the sidebar over here on the left. From there, we're going to choose what hardware we're going to use on our Arducopter FPV drone. So we click on Copter over here on the left, and that takes us to the Introduction to Copter page. Over here, it briefly describes the capabilities of Arducopter within the ArduPilot project. Over here on the sidebar, we have Autopilot hardware options and peripheral hardware. Let's click on Autopilot hardware options to see what flight controllers we have available to use for Arducopter. Similar to iNav, not all flight controllers are able to support Arducopter firmware, so we need to choose our flight controller carefully. Since we'll be building a micro FPV Arducopter, I'm looking for a 20x20 or all-in-one flight controller with a barometer, at least connections for a compass, and at least 1 megabyte of flash memory. Specifically, to support Arducopter firmware, it's recommended you have a flight controller with at least 1 megabyte of flash memory. This is different than your black box flash memory capability you're used to in Betaflight. The more flash memory a controller has, the more Arducopter firmware features it can hold. This page talks about firmware limitations and how on flight controllers with only 1 megabyte in flash memory, reduced firmware is generated that omits less commonly used features. Going back to our hardware options, I was going to go with the Flywoo F745 all-in-one BLHeli32 flight controller, as that's my favorite all-in-one flight controller for many reasons, and I have a few on my workbench. You can check out the video I've done on the Flywoo F745 all-in-one through a link in the video description below. If we click on it and scroll down, we see here that it's listed as having 1 megabyte of flash with this STEM32 F745 VG processor. However, upon closer inspection of the provided documentation with my flywheel all-in-ones and an actual look at the processor chip on board, we see the processor is a STEM32 F745VE, not VG. So if we go to the STEM32 F745 processor product description at this link, which I'll provide in the video description below, we see that the VE does in fact only have 512 kilobytes of flash memory, not the 1 megabyte the VG processor has. With this information, I contacted one of the ArduPilot devs to see if 512 kilobytes was enough even for a reduced feature firmware version. The dev told me it was not enough flash, so my next stop on the list was the iFlight Beast F745 all-in-one board. Although this does have 1 megabyte of flash, it has no compass and no way to connect an external compass. So after more research looking for a 20x20 or all-in-one flight controller with at least 1 megabyte of flash memory, a barometer, connections for a compass that supports Arducopter firmware with enough UARTs for an ExpressLRS or Crossfire receiver, I was able to find this Maytech H743 mini flight controller. This seems to meet all of our requirements with a 20x20 mounting pattern, 5.5 UARTs, to include I2C connections for our compass, a barometer, and 2 megabytes of flash memory with an STM32 H743 VIT6 microcontroller. Even though this H743 Mini isn't listed yet on the closed hardware section of the ArduPilot site, it does state in the product description that it supports ArduPilot firmware with the same target as the Maytech H743. In fact, Maytech's done an outstanding job with the documentation in this flight controller under these tabs here to include providing the ArduPilot firmware on the Maytech site under the Tips tab, and even a troubleshooting site on a known issue which could arise on rare occasions, such as when you interrupt writing to the flash memory, which you should never do. So this is the flight controller we'll be using. For my peripheral devices, I'll be using the Maytech M8Q GPS with magnetometer or compass, along with a V-Fly GPS mate that acts as a standalone isolated power supply for your GPS without the need to power on the rest of your quadcopter's components. This allows for a much faster GPS fix. It's also got a loud built-in buzzer. You can check out a video I've done on this V-Fly GPS mate through a link below. In fact, all of the resources and products mentioned in this video are available through links below. I'll also be using an ExpressLRS ES900 915 MHz receiver from Happy Model. The complete ExpressLRS setup video is also available through a link below. I'll be making this an analog build using my current favorite nano-sized video transmitter, the Immersion RC Tramp Nano VTX, that goes up to at least 500 milliwatts. To get some high-quality cinematic type videos, I'll be using the Cadex Tarsier V2 camera and stabilize the flight videos using Gyroflow, which of course, I have a video on Gyroflow linked in the description below. To make things easier for all of us, I've planned out the build by creating an Arducopter Wiring Diagram, which I've made available to you for download in a link below. This includes connection for an ExpressLRS 900 MHz band, 2.4 GHz band, or even a TBS Crossfire receiver, since they're all connected the same way. The GPS connected to the V-Fly GPS mate, which in turn is connected to the flight controller. The analog video transmitter connection with our Immersion RC Tramp Nano VTX up here. If you were using a SharkBite digital FPV system, it would be connected similar to this by using RX4 in addition to TX4, and by using a 7 to 26 volt power source instead of the 5 volt pad we're using for our Tramp Nano. Our camera is connected up here as shown. In our case, the wires run from the Tarsier board rather than the camera itself. Over here we show the connections for a 4-in-1 ESC to the Maytech H743 mini flight controller. Depending on the 4-in-1 ESC you use, you may need to rewire one of the connectors to make sure the wires going from the ESC socket go to the correct corresponding connections of the flight controller socket. They could be out of order in the JST connector. As an example, you want to make sure VBAT over here on the first pin goes to the far right pin over here on the flight controller, and similarly ground on the third pin over here goes to the ground pin, which is second from the right on the flight controller. In addition to the component's electrical connections, I've included some important highlighted ArduPilot specific notes on the settings we'll need to make in our ArduPilot Mission Planner configurator. These probably don't make any sense to you now unless you're familiar with ArduPilot. However, they will in just a bit, and by including them all in one place on the diagram, It serves as a reminder to make sure they're accomplished. For more information, when you see the text underlined and in a different color, that means it's a clickable link, which takes you to the actual site which covers that feature. I've also included product affiliate links over here on the left, along with their QR codes for easy access to the product descriptions if you're interested in any of them and or would like to support your TMac FPV channel. We're just about ready to flash and configure our Arducopter firmware on our flight controller. To do that, we're going to follow these steps over here on the sidebar. Not all are going to be applicable, so I'm only going to demonstrate those few which are needed for initial Arducopter setup. So we'll start with first-time setup. Install ground station software and click on Mission Planner. That takes us to the Mission Planner homepage, which tells us about some of its features. From here, we're going to go to our sidebar and click on Installing Mission Planner. We're going to download the latest Mission Planner installer from here, and it's downloading over here. Then we're going to cut and paste it into a folder I've previously made on my hard drive, and we're going to double-click on that and walk through the Mission Planner setup wizard. I'm going to click Launch Mission Planner and Finish. And now we've got our Mission Planner software up and running and ready to set up our Arducopter. Before we can use our Mission Planner to set up our Arducopter configuration, we of course need ArduPilot firmware on our flight controller, and we'll get to that in just a second. Right now I want to continue with our first time setup over here on our sidebar. We've installed our ground station software, which is our Mission Planner. So we're going to click on Autopilot System Assembly and Autopilot Wiring, because there's a couple things I want to point out and some concepts I want to introduce you to. First of all, for our Arducopter, we notice a compass is required. That's why we're using the Maytech M8Q 5883 GPS and compass module. Secondly, I want to bring your attention to this note because it sheds some light on how, in general, ArduPilot works. Stay with me on this because this is important ArduPilot stuff. This note states GPS is usually attached to serial port 3 by default in ArduPilot. However, what UART that serial port is assigned to may be different for different flight controllers. This note tells us two things. One, ArduPilot has default expectations of which solder pads our components are connected to, and two, to determine what those defaults are for our specific flight controller, we need to go to our flight controller's documentation within ArduPilot. So let's do that for our Maytech H743 Mini. Since the ArduPilot site doesn't yet have the Mini, but the product description for the Mini on the Maytech site leads us to the same firmware as that for the H743 Wing, we'll click on the H743 Wing. When we scroll down, we get to this default UART order for this Maytech H743 Wing flight controller that maps the serial numbers to the various UARTs. If we compare that to the ArduPilot mapping tab on the Maytech site for the H743 Mini, we see this mapping is the same with two exceptions. One, the Mini flight controller doesn't have a UART3 breakout, which you can see in the product description. And two, Serial 7 for the Wing flight controller has this statement, whereas the Mini on the Maytech site does not. So I've contacted Maytech about this, and Maytech's support informed me this statement also applies to the Mini. So if you're going to use an S-Bus, PPM, DSM, or iBus receiver, you just connect it to the RX pad and it'll work by default. However, if you're going to use Crossfire or ExpressLRS, which we are, we're going to need to set this parameter in our Mission Planner configuration to make it work. What I've just described here is one of the reasons I've placed these notes I referred to earlier on our Arducopter wiring diagram. This ArduPilot default UART order mapping is also the reason we've connected our ExpressLRS receiver up to UART 6 over here, as opposed to using a different UART like UART 7. The word I just used to describe this setting was parameter. Parameters are basically programming statements used within the ArduPilot Mission Planner, similar to CLI commands in Betaflight. These here are three other parameters we're going to set in Mission Planner for our motors and ESC. This top one sets our ESC protocol to DSHOT 600. This bottom one enables ESC telemetry, which this particular ESC supports. And this middle one is supposed to enable automatic mapping of our motors, which would be really nice if it works. All right, that's enough for now about serial ports, UARTs, and parameters. Let's get some Arducopter firmware on our flight controller. Continuing on with our first time setup, we see there are two ways to get firmware on our flight controller. The first way is by using Mission Planner to update the already installed version of ArduPilot on our flight controller. Since our flight controller didn't come with ArduPilot firmware installed, it came with Betaflight, we need to use the second method to get the initial ArduPilot firmware on our flight controller. So we'll click on Loading Firmware to Boards without existing ArduPilot firmware. And we see this involves three things: downloading and installing the driver and flashing tool, downloading the correct firmware for our flight controller, and flashing our flight controller with the firmware. First, we'll download and install the driver and flashing tool called the STM32 Cube Programmer. I'll download the Win64 latest version, which at this time is 2.8.0. It asks you to register by filling out this information, so I'll go ahead and do that. Then it'll send you an email, which you click on the link in the email which was sent, and it'll bring you back to the download site and enable you to download. And as seen over here, it automatically starts downloading for you. And I'm going to move it to a folder which I've already created on my hard drive. Click on it, extract, and then run this setup program. Installation has completed successfully, so we're done. Once it's installed, we can then download our Arducopter firmware for the Maytec H743 Mini, which we can get through the link on the Maytec product description site under the Tips tab we mentioned earlier, or through our sidebar by clicking on Download the ArduPilot firmware. Click on firmware.ardupilot.org, then in our case, Copter. Scroll down to the latest stable version and click on that. Then scroll down to your specific flight controller. For us, that's our Maytec H743. So we'll click on that. And since we're flashing both the bootloader and firmware, we want to download the file with a bl.hex in its file name. Downloading over here. And we'll save that to a location on our computer, which we'll remember because we'll be uploading it here shortly. Before we flash our Maytec H743 Mini with ArduPilot firmware for the first time, I'm going to save all of the Betaflight firmware settings it came loaded with, so I've got them as a backup if necessary in the future. These are basically all of the Betaflight CLI commands or parameters currently on the flight controller. Okay, now it's time for us to flash our flight controller with the Arducopter firmware we just downloaded. So we go over here to our sidebar and click on Upload Firmware to Autopilot. Remembering Autopilot is ArduPilot's name for a flight controller. Per the instructions, we're going to hold down our flight controller's boot button, which is right here on the Maytec H743 Mini, and power it on with USB connection to our computer. Then we're going to open up our device manager. We should see STEM32 bootloader as an indication it's in bootloader mode. We don't. What we see is DFU in FS mode, and I'm hoping that means it's in bootloader mode. We're going to go with that and see what happens. So next we're going to open up our STEM32 Cube Programmer, which we downloaded and installed earlier. And this does in fact seem to be in bootloader mode because we do have USB up here and a USB 1 here. So with USB selected as our connection and this COM port identified, we're going to select Connect. And it did in fact connect. That's a good thing. And our flight controller specifics should appear in this lower right of our screen, which it does. It's got 2 megabytes default. So at this point up here we can open File from this tab and grab the firmware that we previously downloaded to our computer. Double click on it and you see that's loaded up here under the tab now. Then we can select Download to flash the firmware to our flight controller. And we see down here in this window it's working. Download in progress, and once it's done, we're going to disconnect from our STEM32 Cube Programmer and power cycle our flight controller to get it ready to connect to our Mission Planner for configuring our firmware. And here we see that our file download is complete. We click OK, we disconnect from the STEM32 Programmer, and then we power cycle our flight controller. So let's open up our Mission Planner and give it a few seconds to load before we attempt to connect. Close out our STEM32 Programmer. Then with our flight controller connected to the computer through the USB cable, we click Connect. This is the screen that comes up with these 6 tabs across the top. We're currently on the Data tab. We're only going to go through 2 of these tabs today in this video. We're going to use the Setup tab and the Config tab to do our initial setup for our Arducopter by using only a very few of the many options available to us. I'll more than likely go over other ArduPilot features and capabilities in future videos and include those videos in an ArduPilot video playlist I'll link to in the video description below. Let me know in the comments section below if you'd like to see more ArduPilot videos and if you've got specific topics in mind. Let me quickly explain the basic concept of how Mission Planner can be used to set parameters and its similarities to Betaflight and iNav. If we go to our setup page, you'll see a series of tabs over here on the left. This screen is basically your graphical user interface to set some of the ArduPilot parameters available to you. This graphical user interface, or GUI, with its tabs over here, is very similar to the Betaflight configurator with its tabs, or the iNav configurator with its tabs. All three of these software tools are graphical interfaces that allow you to change some settings or parameters on your flight controller's firmware. Notice I said some settings, not all. There are additional settings within each of these firmware, ArduPilot, Betaflight, iNav, EmuFlight, that may not be accessible through the graphical interface. To change those settings in Betaflight or iNav, you need to go through the command line interface, or CLI. In ArduPilot, we can access those parameters through the Config tab, either through the full parameter tree, which lists them all alphabetically, and in drop-down menus, along with a brief description of what each of these parameters do. We can change their settings here, or we can go to the full parameter list, which lists each individual parameter, to me in a more readable format, along with its brief description and the range of values available to you for that particular parameter. We can change their settings here also, and we can also search for a specific parameter we want to change by using the search bar over here on the right. If you have a question about a specific parameter and what you should set it to, I encourage you to use the sidebar in the copter section of the ArduPilot site to find further information about it. Now that we understand a little bit better how to use Mission Planner and that it's very similar to the Betaflight or iNav configurators, just in a different format, let's go ahead and start our Arducopter configuration by using our setup page and going to frame type. Let's use our copter site as a guide over here on the right. We see it defaults to the X configuration of a quadcopter with these motor positions. Take note that these motor position numbers are different than Betaflight. However, the default spin direction, clockwise for this one, and counterclockwise for this one and this one, for the normal prop direction is the same. But what if we wanted to run with our props out, which I normally do? Look at these two diagrams for the Quad X and Quad H. The motor position numbers are the same. However, the motor spin direction is reversed. That's what I want for this build, since I'll be flying props out. So I'm going to change our frame type from X to H. Note, X and H are not interchangeable because the prop rotation changes. At this point, you see I've mounted the flight controller on my 4-inch Cobra frame base plate, and I've connected the GPS with the compass to the V-Fly GPS mate to the flight controller, and also our receiver to the flight controller. The next tab under our Arducopter Mission Planner Setup Mandatory Hardware is Accelerometer Calibration. So let's calibrate our accelerometer using our copter site, first time setup, over here on the right as a guide. If you've got your flight controller board physically mounted with its arrow facing up so you can see it, and forward towards the front of the quad, you're ready to get started with calibration. If, however, you've changed the orientation of your flight controller, mounting so the arrow or the expected front of the flight controller is not facing forward and up, you've got it at a different orientation, then before you do calibration, you'll need to set up a parameter telling Mission Planner what the orientation of the flight control board is. The parameter I'm talking about is AHRS underline orientation, and you need to ensure that that's properly set before doing the accelerometer calibration. You can find this AHRS orientation in our Mission Planner under Config, Advanced Parameters, and then scroll down to Board Orientation, AHRS orientation. And you use this drop-down menu to select the orientation that you physically got your flight controller mounted in your quadcopter's frame. So for instance, this is currently mounted in the correct direction or the expected direction from the manufacturer, but if I were to rotate it 90 degrees to the right so that the USB port is facing forward for some reason, then I would select yaw 90 and so on for whatever orientation adjustments you made from the expected direction of your flight controller facing forward. Then once you've told Mission Planner what the correct orientation of your flight controller is, you're ready to start calibration. So we'll go back to Setup, Accelerometer Calibration, and to calibrate, we just follow the instructions on the screen, which are also indicated in our copter site. We begin with our flight controller level, and we click Calibrate Accelerometer. After it asks you to place the flight controller in the specified position, then you just click this Click When Done button. So right now it's level. I click on Click When Done, and then it asks me to place the vehicle left, as indicated here on our left side. So I move this to the left, like this, and I click Done. And then right, and then nose down, and then nose up, and then on its back. Calibration successful. Great, we've calibrated our accelerometer. The next tab in our ArduPilot Mission Planner is Compass Calibration, and as with iNav, there's two ways to accomplish it. Through USB connection to the computer, which may or may not work due to the computer's electromagnetic interference, or by using your transmitter sticks. Since I want to be able to calibrate the compass using my transmitter sticks if necessary, I'm going to skip over compass calibration for now and do our radio calibration next. If we go to our radio calibration tab, we should see green bars displayed on our channels, and we do not. Why is that? Well, remember from our wiring diagram, we're using ExpressLRS, and there are a few parameters we need to set up in order for our ExpressLRS receiver to work properly with our transmitter. So first we're going to set up our mixer channels in our transmitter for our switches, then set the necessary receiver and transmitter parameters I was just talking about. Then we'll do our radio calibration, followed by our compass calibration. All right, at this point, the only thing I've set up on my model menu for my transmitter switches on my mixes page is I've got my arming switch set up on switch F on channel 5, which is required for ExpressLRS for the arm switch to be on channel 5. I've got my mode switch as a 3-position switch, although ArduPilot can handle up to 6 different modes on a 6-position switch. I've chosen to just use a 3-position switch on channel 6, and that's the switch C up here. On channel 7, I've got return to launch set up, which is over here. And on channel 8, I've got position hold set up, which is this switch on switch G. Now, if you're not familiar with how to set up these switches, I'll just show you one. I'll go to the modes switch, channel 6, press and hold, edit, and I just input my name for that particular action to be located on the switch. Scroll down and select your source, and in this case it's switch C, and it automatically fills it in, and that's it. So that's all I've currently set up in my transmitter. Okay, let's go ahead and set those parameters for our ExpressLRS receiver and transmitter setup. There are those 4 to 6 parameters we need to set up for our ExpressLRS receiver configuration that are located on the wiring diagram. Then there are another 4 we need to set up for our transmitter switches channels we just covered for arm, flight modes, return to launch, and position hold. I'll tell you what I'm going to do to make this as easy as possible for you. In addition to the wiring diagram you can download through a link below that has the ExpressLRS receiver parameters on it, I'm going to include all of the parameters we need to set up throughout this entire configuration. This listing of configuration parameters I'm providing will include the parameter itself, along with the appropriate setting values, the reasoning behind the parameter, along with a clickable link that takes you to the site which has further information on the topic. I'm hoping this will ease your entry into your Arducopter adventure. So for the remainder of this video, we'll be using these configuration parameter charts to set up the necessary parameters within the setup tabs. Let's set up our first 8 parameters for the receiver and transmitter. The quickest and easiest way for me to do that is by going to the full parameter list and using the search bar. Config, full parameters list, search bar over here on the right. So I'm going to type in BRD _alt config, and that's how easy it is to show up. I'm going to set that to 1. Our options are 0 to 10. So I highlight it, I press 1 on the keyboard, and then I'm going to write the parameter, or write parameters, to make sure I don't lose it. And then if we go back to full parameter list, and we type it in again, just to make sure that it took, we see that it's now set to 1. Let's find serial 7 _protocol, and we want to set that to 23 for RC in. Continuing our search, we want RSSI type, _type, equal to 3 for receiver protocol. We want our RC _options to be use path-through extensions for crossfire telemetry, which is this one right here. So we want to toggle this on. So we'll write the parameters. That takes care of our ExpressLRS receiver setup. That wasn't bad at all. Now we need to take care of our transmitter channels and switches. So in our search bar, let's go ahead and change our flight mode to channel 6. FLT MODE _CH6. And as you noticed, it defaulted to channel 5 for copters. We want to put our arm disarm switch on channel 5. _option. And we want to change that to 153. And write parameters. And then we want to change our return to launch on channel 7. So we're going to say RC7 _option. And I'm going to change that to 4. And then position hold on channel 8. So we go RC8 _option. And we want to change that to 69. Now let's go back to our full parameter list. And we see that our change has taken effect. We need to remember to write our parameters. And then power cycle our flight controller. And we'll do that after we disconnect. Now we're ready to do our radio calibration, which is fairly simple. This is sort of the same as calibrating your channel endpoints in the receiver tab of Betaflight. Maybe even easier. We power on the transmitter first. Then we connect our Arducopter to the ArduPilot mission planner and go to Setup, Mandatory Hardware, Radio Calibration. And these green bars should appear. The first thing we want to do is check to see all our channels are mapped correctly. For instance, if I move the throttle stick, the throttle channel is actually the one that moves, which it does. Same with yaw. Pitch. And roll. We also want to make sure the channels for the 4 switches we've set up are working properly as well. Our arming switch, which is on channel 5 up here. Our mode switch on channel 6. Return to launch. And position hold. Good. Now we start our calibration by pressing the Calibrate Radio button and following the instructions on the screen. Make sure our transmitter's on, the receiver's powered, and ensure your props are off. Okay. Click OK and move all RC sticks and switches to their extreme positions so the red bars hit the limits. Okay, so we're going to go ahead and do that. And we're going to go throttle, max min, yaw. Good. Pitch. Roll. And remember, we want to do our switches as well.
TMac GPS rescue engaged.
And those are the 4 switches that we've currently got set up on our transmitter. Then we're going to hit click when done. And ensure all your sticks are centered and throttle is down. Click continue. And here's the summary of our successful radio calibration. And they're right around 1,000 to 2,000, which is good. Now we're done with our radio calibration. All right, now it's time for us to do our compass calibration, and there's 2 ways we can accomplish this. The first way is through connection to Mission Planner through the USB cable in our desktop computer. If that works, the compass calibration is very sensitive to electromagnetic interference, which could result due to its proximity to metal objects or the computer itself. So we're going to give this a shot, but I'm not sure if it's going to work or not. The second, more accurate way to do it is by using your sticks on your transmitter, which is described here. And basically, you start the process by powering up your quadcopter outside after you've got your transmitter turned on, away from any computer devices or things that might generate an electromagnetic field. And to start the process, you hold your throttle stick up and to the right. You'll hear a couple beeps on your quadcopter if it's got a buzzer. And then you just rotate the quadcopter around on each of its axes until the calibration is successfully completed, at which point you should hear 3 tones indicating a successful calibration. For the purpose of this video, we're going to give calibrating the compass a shot on Mission Planner. So let's go ahead to Setup, Mandatory Options, Compass Calibration, and you see up here it's already identified the compass that we've got on our Maytech M8Q5883 GPS and compass module. So to start our calibration, all we're going to do is click Start, and then we're going to rotate the quadcopter around, at which point Mag 1, you'll see a green bar moving across here. And previously when I performed this calibration, it took 2 times for the green bar to move across before we actually heard the tones and got the pop-up window saying successful calibration. So let's give it a shot and see if this works. If it doesn't work, then we'll go ahead and do the stick calibration outside. Get it away from the computer. It's sitting right now on top of the computer. Okay, it's started. So now we're just going to rotate this around while the green bar is moving across the screen. Oh, and we've got successful calibration with 1 green bar. MagCal success. Outstanding. Good stuff. It says to reboot the autopilot, so we're going to click OK. And at this point, we're going to disconnect from the Mission Planner, and then we're going to reboot our Arducopter. And our compass has been successfully calibrated. Outstanding. Next, we're going to set up our flight modes in the ArduPilot Mission Planner. Remember, we have our modes set up in our transmitter on a 3-position switch. So we're going to set up 3 different flight modes. Our 3-position switch will activate positions 1, 4, and 6. Because the low position on our switch is going to end up in this PWM range. The middle position will end up at 1500 or in this PWM range, and the high position will end up above 1750. So at those positions, I'm going to set up Acro on position 6, altitude hold on position 4, and auto tune on position 1. I may go over auto tune in another video. Let me know if you'd like to see that in the comments below. So there's two ways we can set those flight modes. We can use these drop-down menus in the Mission Planner Flight Modes tab, or we can set these flight modes using the full parameter list and in the search bar type FLT mode, and you'll get the results as shown on the screen. For now, we'll use the drop-down menus and select Alt Hold for our middle one and Acro for our last position and click Save Modes. And it's complete. We're good to go. All right, now we're ready to set up our failsafe options under First Time Setup, Configuration, Failsafe Mechanisms. And what we want to do is set it up for a radio failsafe. Takes us to this page, and it talks about when the failsafe will trigger. For instance, if you turn off your transmitter for more than half a second, if the vehicle travels outside of the RC range and the signal is lost for more than half a second, or the receiver loses power. And this is what's going to happen. The copter will take the actions as configured in the parameters described below. And usually with a digital protocol receiver system, it'll send out no pulses, which is this configuration for the receiver, and they call it no signal method. Of note, if the failsafe clears and the transmitter and the receiver do regain contact, your Arducopter will remain in its failsafe mode. It won't automatically return to the flight mode that was active before the failsafe was triggered. So if you set up your failsafe to return to launch and then the signal comes back, it's going to remain in the return to launch mode until you manually switch modes back to Acro mode, for example, if that's what you want to be in. And if you're in Acro mode when it failsafed, then you need to switch it to another mode and then back to the Acro mode. I want to set up the return to launch as my failsafe option. And in order to do that, what we want to do is we want to set this parameter fs_thr_enable, and we want it to enable always RTL with a value of 1 so that it'll switch the Arducopter to return to launch mode. And if the GPS position is not usable in order to return to launch, then the Arducopter is going to automatically switch to land mode instead. So we need to be aware of that. So you obviously want your GPS module working properly when you've got your failsafe as return to launch mode. Now, as with most things in ArduPilot, there's two ways we can accomplish setting our return to launch failsafe method. One is through Mission Planner, Setup, Mandatory Hardware, Failsafe, and we go over to this drop-down menu under Radio, and we select Enable Always RTL. The other method, once again, is through the full parameter list and doing a search on fs_thr, and you'll get the results as shown on the screen. And you set that parameter to 1. We're done with failsafe. Okay, at this point, you see I've got the motors installed now on our Cobra base plate. So it's time to set up our motors mapping and check our motor spin direction. When using BL Heli ESCs, if you set Servo BLH Auto to 1, as previously shown in the wiring diagram, and also included in the parameters charts available through the link below, it's supposed to set up automatic mapping of the motors for the frame class and type you've previously selected. Of course, you'll want to verify this. There's once again two ways I know of to do this. One is through the full parameters list and doing a search for Servo 1 underline function, Servo 2 underline function, Servo 3 underline function, and Servo 4 underline function to make sure they've got values of 33, 34, 35, and 36, not necessarily in that order, depending on your frame class and type that you've selected. The other method is to go to Setup, Mandatory Hardware, Servo Output. Here you can check to make sure positions 1 through 4 have motors 1 through 4 assigned to them in some order. Now, to check to see if they're in the correct order, we can go to Optional Hardware, Motor Test, and using this diagram for our Quad H configuration frame type that we've selected previously, test motors A, B, C, and D to find out which motors actually spin when we press these buttons. Well, for instance, when we press motor A, is it actually motor A that spins, or is it one of these other ones? Then when we do that, we can record the results as I've done in this little spreadsheet. If they're assigned correctly, great. If not, you can easily change the order of them by going back to Servo Output under Mandatory Hardware and reassigning them the correct functions over here through these drop-down menus. So for instance, in my case, and using this spreadsheet, we're going to test each of the motors using these buttons over here to find out which ones spin. First, we need to plug in the LiPo. And then when we press motor A, we would expect motor A over here to spin. This one. Let's see which motors actually spin. That's this motor over here in position 2, also known as motor C for this diagram. So what about if we press motor B? We would expect this one to spin. That one does spin. That's good. Motor C. That one spins, but we wanted this one to spin. And then motor D, we would expect this one to spin. But this one over here in position 1 spins instead. I've already recorded the results. When we select position A, this position spins. When we select position B, that is the one that spins. When we select position C, this one spins. And when we select position D, this one spins. So what we want to do is reorder the motor positions so that they appear like this. Instead of 2, 3, 1, 4, we want 3, 1, 2, 4. So once again, we'll go back to our servo outputs and change 2, 3, 1, 4 to 3, 1, 2, 4. 3, 1, 2, 4. Let's go back here to make sure that they took 3, 1, 2, 4, and that's what we want. So this time when we go to our motor test and we test motor A, I would expect motor A to spin. And it does. That's good. Motor B, I would expect motor B to spin. And it does. Good. Motor C, good. And motor D. Good. So our motor mapping that we've just accomplished is now correct. Another way you can test the motors is through test all in sequence, and it'll spin one up at a time automatically. Or you can also spin them all at the same time. And that's how you do the motor test. What about the spin direction though? Remember in our H frame type that we've selected, these motors are spinning in the opposite direction from the X type, which is what we want because I want to run props out on this particular build. So looking at our diagram, I want motors 1 and 2 to spin clockwise and motors 3 and 4 to spin counterclockwise. By gently placing our fingers on the motors, not too tight because we don't want to inhibit their spin, and then spinning them up with the motor test, we can determine the spin of the motors and match them to this diagram. So if I want motor 1 to spin clockwise, let me go ahead and press my fingers gently on motor 1 and see what it spins like. Now we need to make a note to remember which motors we need to change the spin direction on, if any. So let's go ahead and spin up motor A, and we want it to spin clockwise. And it is. That's good. Motor C, we want to spin clockwise. And it is. Good. Motor B, we want counterclockwise. And it is. Outstanding. And motor D, we want to spin counterclockwise. I think that one's spinning the wrong way. I need to spin that more than 2 seconds. Let me go 5 seconds. Motor D. This one is spinning this way. Motor D is spinning this way, which is incorrect. So we need to change the spin direction on motor D. The rest of the motors are spinning properly. To change the spin direction on any of the motors, if they were spinning the incorrect way, we would do that in the BL-Heli32 configurator, just as we would if we were running Betaflight firmware on our flight controller. So let me go ahead and demonstrate that real quick. So I've opened up the BL-Heli32 configurator, and the way you connect to this is similar to a Mission Planner. Connect your quad to the computer via the USB. And then over here you want to make sure that you select the COM port that corresponds with your flight controller. In this case it's COM14 for me. Yours might be different. And then what you want to do is you want to connect your LiPo to the quad, and then click Read Setup, and it'll read your ESCs. This ESC is showing Rev 32.8. The other ones are showing 32.4. That's because I've just updated this one ESC with the latest firmware. All right, to change this motor's direct spin direction, we need to take a look at the ESC diagram. I've got the power pads facing to the rear, and according to the diagram, we have ESC 4 back here, 2 up here, 3 over here, and 1 up top here. So this is ESC 1 according to the ESC diagram. So we want to change ESC 1 spin direction in BLHeli32. So to do that, we're connected. We go to ESC 1 by right-clicking on it, and we take this slider and move it from normal for ESC 1, drag it over to reversed, and click Right Setup. ESC 1 right, OK. And from there, we disconnect, unplug the LiPo, disconnect the USB, or power down from the USB, close out of BLHeli, open up our mission planner and reconnect the quad to the mission planner. Go back to our optional hardware motor test, and we want this motor, which is, according to mission planner, motor 3D. When we've hit that tab, we want it to spin counterclockwise. We need to plug in the LiPo. Holding my fingers gently on the motor, I'm going to press motor D and see if it spins this way. And it does. Outstanding. We're done with our motor mapping and motor spins. We're good to go. All right, at this point, we're just about ready for our test flight. I've installed the Tarsier FPV HD camera and the Immersion RC Tramp Nano VTX. I've also set up a few more parameters, which I'll display on the screen here for you, and are also available through the wiring diagram and parameters charts through a link in the video description below. These include things like your gyro and harmonic notch filters, Acro settings, and return to home settings. I've set these up using the search bar on the full parameter list in Mission Planner, just like I demonstrated earlier. I haven't yet tuned this quad, so I have no idea how it's going to fly. Before we take her outside for the test flight, I want to point out a few things on the sidebar that may interest you under first flight. There are a lot of pre-arm safety checks ArduPilot goes through before allowing you to arm the quad. If any of these fail, you won't be able to arm the quad. This section tells you how to go about determining which safety checks may have failed. There's also a section over here on how to arm and disarm your Arducopter, to include using the transmitter sticks if you're not arming and disarming using a switch like we've set up on this build. There's some tips on first flights and also a fairly comprehensive pre-flight checklist. I encourage you to take a look at all of these, especially if you're new to radio-controlled aircraft and or ArduPilot. The last thing I want to check before a test flight is I want to make sure I can arm the quad. I'm going to do this while connected to Mission Planner, just in case it fails a pre-arm check, because any failures are going to be displayed up here in this little screen, and you can get further information on them through this Messages tab. See if I can get this in here. This green button is my arming switch, and if she arms, obviously all the motors will start spinning. I've got air mode on. All right, here we go. If she arms, we're good to go for our test flight. Nice. Okay, the first thing I'm going to do is hover this thing for about 30 seconds or so, check the motor temps, make sure that they're not too hot. It's something I do with all of my builds. I've also determined that the ArduPilot default PIDs are set up for 10-inch quads. This is a 4-inch micro, so I have had to change the PIDs to some degree. This is a basic PID tune, just based on my observations of what I could hear with regards to the motors. I haven't done any data flash logging, and I haven't done any auto tune on this. But the basic PID tune that I've got on this right now, I'll go ahead and put on the screen in case you're interested. All right, let's give this a shot. Got it in Acro mode. I'm gonna hit the arm switch and just hover for a little bit. Seems to be flying pretty good. Basic tune. too bad based on just what I could see. It'll be interesting to see what the auto tune is able to do. Just a few more seconds and then I'll check out the motor temp. Looks like it's flying pretty smooth though. These are all good. All right, now what we're going to do is test out both altitude hold and position hold modes. Then we'll take her somewhere else to check out return to launch. I'll first go into altitude hold mode by flipping this switch to the middle position.
Altitude hold engaged.
And we'll see how well she holds her altitude. Then I'll flip this switch over here on the right all the way down for position hold.
Position hold engaged.
And see how well she holds her position in three-dimensional space. Now the way altitude hold works, and this applies to stabilized mode as well, is the throttle needs to be within a certain range of its mid position in order for the quad to hold its altitude. I've got my range set up to be within plus or minus 20% of mid throttle. You can still move the quadcopter up and down using your throttle if you're outside that range. You can also continue to position the quad as you normally would using your transmitter sticks to adjust your position if necessary. So that's how it works. Let's give these autonomous modes a shot and see how well they do. All right, first we're going to try altitude hold. Remember, we can position it using our sticks. Something's off the throttle. Looks like it's maintaining the altitude pretty good at about 6 meters. Nice. All right, how about position hold? Let's scoot out here a little bit further. Maintaining its position. A little bit windy out here today. See how it corrected itself? Nice. Doing a good job in the wind. All right, I'm impressed. Time to bring her in. All right, what we're going to do now is try out the return to launch mode. This is going to be the first time I've tried it, so I have no idea what's going to happen. But the return to launch switch is going to be over here. I'm going to fly out in Acro a couple hundred meters and then flip this switch all the way down. And hopefully the quadcopter is going to gain altitude to about 35 meters, turn around and come back and land near here. We'll see what happens. All right, here we go. Coming back.
I see it.
Not bad. That's going to do it for today. I hope you found this useful for starting your ArduPilot and Arducopter adventures. Thanks for your time. I'll catch you next video. Clear skies, friend.